Hello everybody, today we are going to solve this one-dimensional physics question here today. The question is, a stone is dropped into the water from a bridge 44 meters above the water. Another stone is thrown vertically downwards 1.0 seconds after the first stone was dropped. Both stones strike the water at the same time. What was the initial velocity of the second stone? Okay, so let's draw what is happening here. There is a bridge here, and this bridge is 44 meters high. We have one stone here, stone A, that is dropped downwards, and stone B is thrown downwards. So there's some initial velocity here. So let's write down everything that we know about stone A and stone B. Okay, so there will be an initial velocity for stone A. There will be a final velocity for stone A. There will be an amount of time that it takes stone A to reach the bottom. There will be the distance that stone A travels, and stone A will have a certain acceleration as it falls down. And we'll have all of these same values for stone B. So stone B will have an initial velocity, a final velocity, the amount of time that it takes stone B to fall, the distance that stone B travels, and the acceleration of stone B. So let's write in which of these we know and which of these we don't know. So let's start with stone A. What is the initial velocity of stone A? Well, it says a stone is dropped into the water. So this stone is being dropped from a stationary location. So that means that it has no speed. So this is 0 meters per second. Now, what's the final velocity of stone A? That is how quickly stone A is moving once it reaches the bottom, just before it reaches the bottom. So this, we don't know what this value is right now. We can calculate this if we'd like to, but right now we don't know what this is. So time A, how long does it take stone A to reach the bottom? That we don't know, so let's just leave that as t right now. We could leave that as a variable. Okay, how about the distance that stone A travels? Well, stone A goes 44 meters downwards, so we could say that that is 44 meters. And we could keep this positive because we could just assume over here that downwards is positive, just to keep things simple. Okay, and how about the acceleration of stone A? How quickly is stone A gaining speed as it moves downwards? Well, we can assume that this is taking place on Earth, so we could say that the acceleration is 9.81 meters per second squared. Okay, so this is what we know about stone A, so let's take a look at what we know about stone B. So what is the initial velocity of stone B? Is it also 0 meters per second? Well, the answer is it's not also 0 meters per second. It says another stone is thrown vertically downward. So if it is thrown downwards, that means that it has some initial velocity downwards. So this is some value, but we don't know what this value is. And actually, this is what the question's asking for. The question is asking, what is the initial velocity of the second stone? All right. What about the final velocity of the stone? Do we know how fast the stone is moving once it reaches the bottom? Again, that's something that we don't know. The next variable is the time. How long does it take stone B to reach the bottom? Well, we know that both stones strike the water at the same time. And we also know that the second stone is thrown vertically downward 1 second after the first was dropped. So we know that the time that stone B is falling is 1 second less than the amount of time that stone A is falling. So we know that stone A, we said that that was falling for t seconds. So this will be 1 second less than that. So we could represent that as t minus 1. Okay, how about the distance that stone B falls? Well, that is going to be the same. It's also falling this 44 meter distance here. So that's 44 meters. And what about the acceleration of stone B? It's going to be the same value. It's going to be 9.81 meters per second squared again, because we're assuming that this is taking place on Earth. Okay, so there are going to be certain equations that I assume that you know. So I'll write these equations right here for us. So there are two equations that I'm assuming that you know, and we'll use these equations to solve what we need in this question. The first equation is average velocity times time is equal to distance. And we can represent average velocity as initial velocity plus final velocity divided by 2. So this equation becomes initial velocity plus final velocity over 2 times time is equal to distance. Okay, so here's the first equation that we're going to be using to solve this question. The second equation that I'm hoping you know is that acceleration is equal to change in velocity divided by time. So we can represent that as final velocity minus initial velocity divided by time. So here are the two equations that we're going to be using. Okay, so let's get started. And let's start by taking a look at stone A over here. So we can use this first equation that we have here, average velocity times time is equal to distance. And let's see what we could solve for stone A using this equation. So we have stone A's initial velocity plus stone A's final velocity divided by 2. So this is just equal to the average velocity times the time that stone A falls is equal to the distance that stone A travels. Now, let's take a look at how many unknowns we have in this equation. What do we not know? Okay, so the initial velocity of A, we know this value. We know that this is 0. Final velocity of stone A, we don't know that, so that's one unknown. We don't know what t is, so that's 2 unknowns. And we know the distance that stone A travels, that's 44 meters. So with this one equation, we have 2 unknowns. So we have to get rid of one of these 2 unknowns to be able to solve for something, because we can't solve for 2 unknowns with only one equation. So let's take a look at this equation. Let's isolate for final velocity. So final velocity will be equal to acceleration times time plus initial velocity. And this can be useful to us in this equation here. Wherever we have final velocity in this equation, we can replace that with acceleration times time plus initial velocity. So let's do that right now. We have initial velocity of stone A plus, and right here we have final velocity. So remember, wherever we have final velocity, we're going to replace that with acceleration times time plus initial velocity. So we'll do that right here. So we'll do acceleration times time plus initial velocity. And now we'll just continue with the rest of this equation divided by 2. Over here this is times t is equal to the distance that stone A travels. So in this first line here, we had 2 unknowns in one equation. We had final velocity was unknown and time was unknown. So with this second equation, we isolated for final velocity and replaced that with these terms here. And now in this equation, we only have one unknown. The only unknown here is time. So we can just simply solve for time. So let's solve for t. Let's expand this out. So we have 2 initial velocities here. So we can write that as 2 times initial velocity of stone A. And of course that's going to be multiplied also by t plus acceleration times t squared. And that's all going to be divided by 2, and that will be equal to the distance that stone A travels. So let's continue isolating for t over here. So we could bring this 2 from the denominator here to the other side. Then we have 2 times the initial speed of stone A times t plus the acceleration of stone A times t squared is equal to 2 times the distance that stone A travels. Now we know this value here, the initial velocity of stone A. What's this value? This value is 0 here. So this whole term here just ends up becoming 0. So we have at squared is equal to 2 times the distance that stone A travels. So solving for t ends up becoming 2 times the distance that stone A travels divided by A, and you take the square root of all of that. So let's plug in these values and see what we get for t. So 2 times, what's the distance that stone A travels? That is 44 meters. Divided by the acceleration, which is 9.81 meters per second squared. Take the square root of all of that, and we can see that the units work out. We have the meters and meters cancel out, and we have seconds squared on top. Square root of seconds squared is just seconds. So the time is equal to 2.995 seconds. Okay, so we now know, and this is time for stone A. So we know how long it takes stone A to reach the bottom now. So since we know how long it takes stone A to reach the bottom, we now know how long it takes stone B to reach the bottom, because stone B is falling for 1 second less than stone A. Because remember, stone B is thrown 1 second after the first was dropped. So let's see what we can do for stone B now. So let's start with this same equation that we had up here. Average velocity times time is equal to distance. So let's take a look at stone B now. We were looking at stone A earlier. Now let's take a look at stone B. So average velocity is equal to initial velocity plus final velocity divided by 2. And if we multiply this by time, that is equal, and this should be time B because we're taking a look at stone B right now. Then this will be equal to the distance that stone B travels. So let's see, how many unknowns do we have in this equation? Time B, it was unknown before, but now that we've solved for what time A was, we know that time B is just 1 second less than that, so it'll be 1.995 seconds. So time B is not an unknown anymore. The two unknowns that we have are the initial velocity of stone B and the final velocity of stone B. We could see that we don't know what either of these are. And the distance that stone B travels, that's something that we do know. So again, remember what we did last time. We took a look at the second equation that we should know, and we isolated for one of the terms that we didn't know. We plugged that in, and then we were able to have one equation with one unknown. So let's do that again. So we'll do the exact same thing here. We've already isolated for final velocity. So wherever we have final velocity, we can replace that with acceleration times time plus initial velocity. So let's do that in this equation right here. So we have initial velocity of stone B plus, now we have final velocity of stone B. Oh, I did these letters here wrong. Okay, there we go. Now these letters are fixed. Yeah, this should have been final velocity of stone B. So we now have final velocity of stone B here. So wherever we have final velocity, we'll replace that with acceleration times time plus initial velocity. So let's do that. So acceleration time of stone B plus initial velocity of stone B. And this all here is divided by 2. Multiplied by time that stone B is falling for is equal to the distance that stone B travels. So how many unknowns do we have in this equation now? The only unknown that we have is the initial velocity of stone B. So let's isolate for that, and then we'll be able to solve it. Because remember, this is what the question is asking for. What was the initial velocity of the second stone? So let's solve for that right now. So we'll have inside the brackets here, we'll have 2 times initial velocity of stone B, because we have 2 of the same terms being added together, plus acceleration times time B. This is multiplied by time that stone B is following. We could bring this 2 on the bottom up to the other side, so we have 2 times the distance that stone B travels. Okay, so let's continue isolating for the initial velocity of stone B. So we can multiply this time B into here. So we have 2 times the initial velocity of stone B times the time that stone B is falling plus acceleration times the time that stone B is falling squared is equal to 2 times the distance that stone B travels. So this term here doesn't have any of the initial velocity of stone B, so we could just bring that over to the other side. So velocity, or sorry, let's write it like this: 2 times the velocity of stone B initially times time B is equal to, then we have, this stays the same here, whoops, and then we just subtract this term because now it is on the other side, so that is time B squared. And to get the initial velocity of stone B on its own, we'll just divide both sides by 2 times the time that stone B falls. So the initial velocity of stone B is now equal to 2 times the distance that stone B travels minus acceleration times the time that stone B falls squared, all divided by 2 times the time that stone B is falling. Now everything here is known, so we should be able to just plug in these values here and we can solve for what the initial velocity of stone B was, which is what the question is asking. So let's plug in these values here. What do we get? We get 2 times this value here. How far did stone B fall? Remember, that was 44 meters, minus the acceleration is 9.81 meters per second squared, because we're assuming that we're on Earth, times what was the time that stone B was falling for? It's 1 second less than this. So we didn't write this down anywhere, but just know that time B is 1 second less than this. We know that from this right here. Time A is equal to t, and time B is equal to t minus 1. So this is equal to 1.995 seconds squared divided by 2 times, and again, this same time B value, 1.995 seconds. Okay, and it looks like all the units here make sense. We have meters on the top here. Over here we have meters per second squared multiplied by seconds squared. So we have just meters on the top, just seconds on the bottom. So speed is in meters per second. So it looks like our units here are good. So our final value for the initial velocity of B, if we put this into the calculator, is 12.3 meters per second. So this is the answer to the question. The question that was asked was, what was the initial velocity of the second stone? Here's how we calculated it. The initial velocity of the stone was 12.3 meters per second downwards. So I hope that this video was helpful to you, and I'd love if you could share this video with anyone who you think it might benefit them. And I hope to see you in future videos, so take care.